What are we measuring when we're measuring temperature?
Energy?
Okay.
So the excitement of the atom?
Speed.
Speed. When you think about measuring something's temperature, you're going to put the thermometer in there, or whatever it is that you're using, somehow measuring the actual speed at which those atoms or molecules are moving. They're going to be vibrating in place. If they're a gas or a liquid, they're going to be slamming all into the thermometer or whatever it is. But we're really just saying, how fast are these molecules moving? Okay, so this one here, I want to know about heat. And what I've got are some degrees C, grams, cals. And we said this was aluminum. And there's a mass there. So what unit am I looking for when I'm trying to answer this question about how much heat was added? I'm looking for calories. So I've only got one thing up here that's got calories in it. And remember, this type of problem is about I put some heat in or change something in some manner, and there's always going to be an initial and a final temperature. And that can't be in the railroad track thing, so we can do that outside of it. So I've got its final temp is 110, and it started at 3 degrees Celsius. So did it gain 110 degrees of temperature? It only gained 107 degrees. Okay, so I'm going to start. Why did I start with this here first? I have my calories right where I want them. So now all I need to do is cancel out that grams and that degrees C. So I have 75 grams there. There's the 75 grams. That's gone. And I've got my change in temperature, which was 107 degrees Celsius. And so what do we got here? Oh, that's totally not it. All right, so 107 times 75 times 0.22. Okay, is that good?
That's sig figs.
Yeah, what do I need to do? 1,800 calories would be correct, because I've only got two significant figures in that 75. I've got 2 sig figs in this degree C here, and that guy there. So yeah, it needs to be in 2 sig figs. Okay. So I didn't see anybody ask any questions about this one, so I thought it was hard, but it must have been pretty easy for you, right?
That was hard.
It was hard? All right. So I think the best thing to do with a problem like this is to initially like draw yourself a little diagram or whatever. So I've got myself a chunk of lead, and that chunk of lead's going to go into a container of water, and then eventually that chunk of lead's going to be down here at the bottom. Okay, so it's a hot chunk of lead. So this chunk of lead is going to go into this water, and what's going to happen to the water's temperature?
It's gonna rise.
It's going to rise. When's it going to stop rising? This is a very important question.
When the lead and the water have reached equilibrium,
So what's that mean?
they're equivalent temperatures.
They're the same temperature, right?
Right.
They have the exact same temp. So that lead keeps, the lead's atoms are moving really fast because it's at a high temperature. You said it was hot. It goes into the water. The water's molecules aren't moving as fast. And the water molecules are running into the lead, and then they're being thrown away at a much higher speed. So they heat up. They're actually moving faster. And then eventually, the speed at which the lead molecules and the speed at which the water molecules, that all evens out. They're not moving exactly the same speed because they have different masses, but the lead atoms have done what?
Cool down.
Cooled down. What'd you say?
Liquefied?
No.
Slow down.
They've slowed down, and the water molecules have sped up. So when we're thinking about change in temperature, that's what you should think about. What do we got here? Start water started at, it's now at 22. So what I know for this problem is that the lead is 75 grams and the water is 175 grams. And the water was at 11 degrees Celsius and now it's at 22 degrees Celsius. Do I know anything else knowing that information?
It heated 11 degrees.
Okay, so it's changed in temp. The water's changed in temp is 11 degrees. Something else we should know based on what we just talked about.
You know how much the lead, lost, how much heat it lost?
I don't know that yet, but I will know that eventually.
We know that we can convert the amount of temperature change in the water to a calorie number. So we have a number that we can use to find our calories.
Okay. I'm talking about a piece of information I just know without doing anything at all, based off of what we just talked about. This 22, what is this a measure of?
Temperature,
Okay. Whose temperature?
the water,
Is that it?
and the lead.
And the lead, right? The water heated up and stopped heating up at 22 degrees because the lead's temp was high and it stopped falling when it hit what? 22 degrees. So I also know the lead's final temperature, which I'm gonna definitely need to know so I can calculate its initial temperature. So somebody had said earlier that we could calculate how much heat the water gained. Absolutely true, so we can go ahead and do that. So I need to know the heat the water gained, so I'm just gonna use Q, and then it's 1 calorie per gram degrees C. Where did I get that from?
The specific heat of water.
Yeah, it's a specific heat of water. I mean, you don't need to know it, but it's easy. It'll be on the test. I mean, as far as this is the specific heat of water. Okay, so I need to cancel out the grams, so I'll put 175 here. Grams cancel. And then what I'm going to use for my change in temperature value, I'm going to cancel out that C on the bottom. What's this 11? It's the 22 minus the 11 giving us 11. Okay. So I've got 175 times 11. So I get 1,925 calories. Don't sig fig the thing, because this isn't what anybody was asking you about. Just keep all of these numbers. The only time you sig fig is when I answer the question, which is what the initial temperature is. That's when I'm going to take care of that. Okay, so I know that this water heated up, it gained 1,925 calories of energy. Do I know anything else? Now that I know that?
That's how many calories lead gave?
The lead what? Lead lost, right?
Yes.
So the lead was hot and it cooled down. So as it cooled down, it gave its energy away. And how much energy did it give away? 1,925 calories. So, yeah,
Why is that not negative?
I was just getting to that. So is it 1925? No, it's
Negative.
negative 1925. So if this Q right here, this 1925 is the Q of the water molecules, in this particular instance, the Q of the lead is going to be negative 1925 calories. And is everybody okay with me saying that? It lost that much heat. It's totally fine for something to have negative heat because it's just meant that it gave it to something else. Okay, so what I need to do is calculate out a change in temperature. Because what I have is the final temperature for the lead, and I need its initial temperature. So if I can get a change in temp, then I can get my initial temp. So I will, this is lead, right? Oh, I gotta look that up. What is lead? Somebody have lead specific heat?
038?
All right, I'm okay with that. 0.038 calories per gram degrees C. All right, so I need a temperature value, so I'm going to write grams degrees C 0.038 calories. Why? Why am I writing it like that?
Proportion uneven, it's on top.
I want Celsius. I want Celsius in my answer, and I need my answer to have that Celsius unit in the numerator, so I flip the thing over to give me the unit that I want where I want it. So now I need to get rid of the calories and the grams. So the calorie value, how am I going to get rid of that? that unit?
Use the negative 19.5.
So if I use negative 1925 calories here, all right, so now the calories are gone. Now what can I do?
75 grams on the, in the denominator.
So that's the mass of my lead, and now that's gone. And so what I'm going to do is calculate out a temperature. So divided by 0.038 divided by 75. I get negative 750 degrees C. Okay. So, am I done? What is this?
It's a difference.
Okay, so tell me what that negative 675 is.
Lead.
The heat of the lead? No, that's calories.
The amount that the lead dropped.
The temperature drop of the lead. The lead was hot. The lead was, it actually lost 675 degrees of heat. So, do we know what its initial temperature was? Yeah, we can know.
Yeah.
So the equation for change in temperature is temperature final minus temperature initial. So what pieces of information do I know in this little equation?
The final.
I don't know the initial. I'm looking for the final. I know the final temperature, and this is 22 degrees Celsius, right? Because that's what the water's temperature ended up being. So this guy here is 22 degrees Celsius. I'm actually looking for the temperature initial, and then the change is negative 675 degrees C. So I add temperature initial to both sides. I add 675 to both sides. I get temperature initial is equal to 22 degrees Celsius plus, it's plus because it'll end up being, I'm adding it to both sides, so 675 degrees C. And so what is that, 697, is that right?
That's right.
Degrees C. Okay, so sig figs, how many do I get?
1,
One?
2.
2, yeah. Why one? Okay. I'm fine with that answer. Okay, so how do I manage this 697 if I gotta use 2 sig figs? Because what happens if I write 700? It looks like 1, right? So what do I do?
700 point.
Nope, because then that's 3.
3 because it makes a 0 significant.
How about 7.0 times 10 to the second degrees C? That looks like 20. Let me make that tinier. Why is this the best way to do this?
I guess because it's accurate.
That's telling you 2 sig figs for sure, right?
Right.
And it's telling you 700. Okay. That one was great, right? You want like 20 of those for the exam? Okay. How about this one here? Why should you not be super happy about this?
Because it's a
Because
great
it
year
takes
for a
longer,
Mustang.
yeah.
What?
It's a great year for a Mustang.
Okay, so you should be totally happy that you're driving a 66 to 89 High Pro, but you can't really use it. Why?
Just traveling I-84 basically.
A little bit better, but pretty much that's about it, right? So this 125, there's no unit with that, but what unit should it be?
Kilometers.
Yeah, so 125 kilometers per hour is not miles per hour. And so in 1966, do you think they were putting miles per hour and kilometers on the speedometers?
No.
Nope, I had one. It did not have it. It just has miles per hour on it. So 1 kilometer is 1,000 meters, and 1 meter is 100 centimeters. And there are 2.54 centimeters in 1 inch, and there are 12 inches in a foot, and there are 5,280 feet in 1 mile. So 125 times 1, 2, 3 times 1, 2 divided by 2.54 divided by 12 divided by 5,280. Yeah, 77.7 miles per hour. So, barely better. Well, I guess, does 84 turn to 75 miles an hour somewhere?
So people exceed it all the time, so.
Yeah.
Oh, it's about to turn to 70 from North to Dallas to Idaho.
Yeah.
Oh, I didn't know that.
They're raising.
Okay.
Like 197.
Has anybody tried to buy gas yet? Or, sorry, pump their own gas yet?
Yeah.
How's that
In
gone?
Washington,
I live in Washington, so yeah.
No, I'm talking about Oregon.
Oh, really? They don't like it.
Well,
Well, you do it at night.
after 6 p.m., between 6 p.m. and 6 a.m., if the person's not standing right there, you can just do it yourself.
Really?
In Hood River County, in any county that's got less than 45,000 people in it, and Hood River definitely has less than 45,000 people.
Yeah, they usually get
No.
gas.
So you're telling me you're stuck at living in either Oregon or Jersey?
Yeah.
Those are your options?
Yeah.
Okay, all right. A whole bunch of cool stuff started happening on the 1st. You guys really should like find that in the paper. Some like really cool stuff. Okay, so tell me what this minimum case volume would need to be to make sure that this phone does not find its way to the bottom of the Columbia.
less than
Right.
The phone's volume needs to be less than 1 milliliter.
No.
case.
Yeah,
The density needs to be less than 1. Okay, but the question is, what's the case's minimum volume?
but you have to take the masses and add the phone and the case together.
Okay,
Take
great.
the mass and the case
So
and put them together.
I got 180. So the phone and the case together have a mass of 180 grams. 180 grams of phone plus case. So now what?
So now we need to find, well, I guess now we just need to know that the density has to be less than 1 for that thing to float.
Okay. So then the case volume would need to be what?
Less than 1.
No.
181.
Oh, yeah.
181 milliliters? That'd be fine. If the case's volume is 181 milliliters, the volume is larger than the mass, and then this thing's gonna float. Everybody okay with that? So what happens if the case volume is like 150 milliliters? Sinks pretty fast, actually. I can attest to that. There is a perfectly good S4 iPhone somewhere on the bottom of the Columbia in an incredibly good, expensive waterproof case. Sad. So, somewhere near the spit. How about this magnitude of the charge of the proton and the charge of the electron?
They're equal.
We okay with that?
Yeah.
So I know that the proton is like 2,000 times bigger, but its plus and the electron's minus cancel each other out. Exactly. What's Dalton saying has happened during a chemical reaction?
Atoms rearrange themselves.
Yep. Nothing else. The atoms simply rearrange themselves. They can't turn into different atoms. Nothing can happen to the atoms. They just let go or combine or just simply rearrange how they're connected to each other. But the atoms themselves are perfectly as themselves. Why is he all happy that water's formula is H2O?
It never changes.
Okay, so it's always H2O. I like that. What else?
You wouldn't want to drink HO2.
I'm not going to write that. Something else?
Because it proves that atoms don't change with reactions.
They're only small numbers,
Okay.
and the first one to, they're already done.
Yeah. He was saying that, okay, so if it is H2O, then there are 2 H's and 1 O, and that's it. And there's never a half of an O and one H. That's not a possibility. It's two H's and one O. Has to be. How about this defending matters mostly empty space?
Because of the space in the atoms themselves.
Okay, sure. So if the nucleus, what's the size of the nucleus? Anybody remember?
Uber tiny.
About 10 to the negative 15th meters. So very small. And then the atom, anybody remember the atom size? 10 to the negative 10th meters. So what's the difference between those two things?
5 magnitudes.
100,000. 5 zeros, right? So 5 zeros bigger. So I've got this tiny speck of mass, and the thing that it's sitting in is 100,000 times bigger, and there isn't anything there except a few electrons randomly flying through. So this is very analogous to, we have comets and just various, what want to say, celestial bodies float through the solar system all the time. How often do they hit the sun or a planet? Not very often. Why? It's mostly empty space, right? It's almost all empty space. Did anybody see what Hawking said last week? Stephen Hawking? Based off of geological and astrological data from Earth and the Moon and a couple of other places, that we're right in the time frame that every 10,000 years something awful happens. Like we're going to get sprayed with asteroids or something like that.
That makes me feel good.
Yeah, he was trying to tell everybody, let's speed up this whole, like, make it to Mars thing, because we need to have people in both places. What did Thomson contribute?
It discovered the electron.
Yeah.
Okay, so one, there's a, what else?
Yeah, sorry. You got plum pudding model, right?
Not actually true, though.
But he had the negatives can come off.
Okay. Anything else? So he determines that there's a positive and negative portion to the atom, and the negatives can come off, and the positive has to stay put. They ended up calling that thing that can come off the electron. That's not what he called it, but it's all right. So what did Rutherford contribute? That's still a true thing.
He came up with the idea of the nucleus.
Okay, so he came up with this nuclear model of the atom. So that positive we're going to collapse all of that positiveness down to a tiny, dense nucleus. How about Soddy? What was his deal?
You worked with Thompson,
Rutherford.
or, yeah, Rutherford.
They did get gold as well altogether, yeah.
Yeah.
So when Rutherford came up with this, they were thinking that the nucleus portion was just a chunk of positiveness, like one body. And it turned out Soddy was like, no, it's individual bodies, individually positively charged that all come together. And Chadwick?
He found the neutron.
Found What do you think the neutron's purpose is? So if I'm talking about a lithium atom, there's 3 protons in the lithium atom's nucleus, right? So those things are all positively charged. Have you ever tried to put 2 ends of a north pole of 2 different magnets together? What do they try to do? Push away. So what do you think 3 protons would want to do? Push away. So what I do is I shove some buffer stuff in between there. So if you took those 2 north poles of a magnet and instead of putting them right on top of each other, instead you put a book in between them, could you push them together up against the book and they'd still have that book buffer? So that's what's going on here. I put the neutrons in between, and the protons don't actually have to physically sit right on top of each other. I put something in between them so they don't have to actually touch. And what you'll see is the more protons that things have, the more neutrons that need to go in to provide that buffering. What was Bohr's contribution?
Planetary model.
Planetary or the solar system model? Sometimes this is a real good way to describe it, but it turns out it's not completely accurate. So what did Heisenberg do?
You know, the secondary model, right?
So what's his model?
The Heisenberg model.
It's not the Heisenberg model.
He uses math to estimate where the electron will be.
Okay.
Yeah, he
Anybody got a
projects the location.
name?
That resemble the sun,
No, it does not.
but is it,
It's like a cloud.
Like hundreds of numbers, you can see those like a
Quantum.
Quantum mechanical model and statistics and math. That's how he came up with the theory. And we're still using this one. 80-ish, 70 years later. Nobody's come up with anything better.